Hello everyone, I'm Shane, and today I'll present my lab analysis of projectile motion using experimental and computational models. We'll cover key physics concepts, our setup, simulations, and compare results. Let's start with the lab's purpose. This lab investigated projectile motion through experiments and simulations, analyzing how well physics-based models predict real-world motion. We focused on Newton's second law, momentum, and air resistance. We collected real-world data, compared it to computational models, and observed air resistance impact. Before discussing the experiment, let's review key physics principles. Projectile motion follows Newton's second law. Acceleration depends on force. Without air resistance, gravity is the only force, creating uniform downward acceleration. However, drag force opposes motion, altering the trajectory. Drag is proportional to velocity squared, meaning faster objects face greater resistance, leading to effects like terminal velocity. Now, let's look at our experimental setup. We used a small paper ball launched from a certain height with a mass of about 0.005 grams, a stationary camera, and a reference object, which was a meter stick, ensured accurate motion tracking via tracker software. Next, let's examine our collected data. Using Tracker, we extracted position data and generated a trajectory graph. This visualizes velocity changes over time and how air resistance influenced motion. Now, let's compare with theoretical predictions. We first simulated motion under gravity alone using GlowScript. The trajectory was perfectly parabolic, but real-world motion is rarely this ideal due to additional forces. Next, we incorporated air resistance. Adding drag force refined the simulation, opposing motion and shortening the projectile's range. This model better reflects reality than the gravity-only version. Let's compare all models with experimental results. This graph overlays experimental data, the gravity-only model, and the drag-inclusive model. The gravity-only model overestimated range, while the drag model aligned better with real data. Minor discrepancies stem from experimental errors and model simplifications. Now, let's examine sources of error. Errors could stem from camera calibration, variations in launch technique, or assumptions about the drag coefficient in simulations. To improve accuracy, refining drag coefficient estimation and using higher resolution tracking could help. Let's explore a what-if scenario. What if the object was thrown straight up instead? The total flight time would increase, as it would first decelerate before falling back. Equations of motion confirm this difference. Now let's summarize our key takeaways. This experiment demonstrated that computational models effectively predict projectile motion, but air resistance must be considered for accuracy. It alters the trajectory by slowing motion and reducing range. Future improvements could refine drag coefficients and use more precise motion tracking. Thank you for your time.